In this video, we're going to talk about friction. The questions that we're interested in is what is the difference between static and kinetic friction? What is a coefficient of friction, and why does air resistance depend on the size and shape of an object? Friction refers to an ever-present resistance to motion that occurs whenever two materials or media are in contact with each other. This resistance occurs for all types of media, solids, liquids, and gases, and is characterized as a force of friction, denoted with a lowercase f. In many physics examples, for simplicity, we generally ignored friction forces. Now that we know how to describe motion, we are more ready to consider situations that are more realistic. In that, the effects of frictions should be included. In some situations, an increased friction is desired. For example, when you put the sand on an icy road or sidewalk to improve friction or traction. This might seem contradictory since an increase in friction presumably would increase the resistance to motion. We commonly say that the friction opposes motion and think that the force of friction is in the opposite direction of the motion. However, consider the forces involved in walking. The force of friction does resist motion, that of the boot, but is in the direction of the walking motion. Without friction, the foot would slip backward as when walking on a slippery surface. So there are situations where friction is desired and situations where reduced friction is needed. Another situation where reduced friction is promoted is in the lubrication of moving machine parts. This allows the parts to move more freely, thereby lessening wear and reducing the expenditures of energy. Automobiles would not run without friction-reducing oils and greases. Friction between solids is generally classified into three types: static, kinetic, which is also means sliding, and rolling. Static friction includes all cases in which the frictional force is sufficient to prevent relative motion between surfaces. Suppose you want to move a large desk and you push on it, but the desk doesn't move. The force of static friction between the desk's legs and the floor opposes and equals the horizontal force you are applying. So there is no motion, a static condition. Static comes from the word stationary, static condition. Kinetic friction or sliding friction occurs when there is a relative sliding motion at the interface of the surfaces in contact. When pushing on the desk, you can eventually get it sliding, but there is still a great deal of resistance between the desk's legs and the floor. That is when you say there is a kinetic friction. Rolling friction occurs when one surface rotates as it moves over another surface, but does not slip or slide at the point or area of contact. Rolling friction, such as that occurring between a train wheel and a rail, is attributed to small local deformations in the contact region. This is type of a friction This type of friction is difficult to analyze and will not be considered. Now let's take a look at the forces of friction on stationary and sliding objects. These forces are called the force of static friction and a force of kinetic friction, respectively. Experimentally, it has been found that the force of friction depends on both the nature of the two surfaces and to a good approximation to the normal force. So the friction force depends on the normal force. The force of static friction, Fs, well, let's not write the vector because we want to talk about the magnitude, between the surfaces in contact acts in the direction that opposes the initiation of relative motion between the surfaces. The magnitude takes on a range of values, which we can write in form of an inequality, and that equals some kind of coefficient times the normal force. We put a little subscript s here, which is known as coefficient of static friction. It is important to notice that the mu s, our coefficient, is dimensionless. As you can see on the left side of this inequality, we have a force that is measured in newtons. On the right side, we have a normal force that is also measured in newtons. So the mu s has to have no dimensions. And it is, since it is the coefficient of between two forces, that is just a number. So let's understand the mu s. How do you write that? It's a Greek letter, mu, and usually it is on the row. It looks like this. Some people just write like this, but this is not correct because this is English letter U. So we're talking about Greek letters, which has little longer tail, and then it looks like a U after that. So make sure that you learn this, and it is pronounced as mu. Okay. Now let's talk about this less than or equal sign. What does it indicate? It indicates that the force of static friction may have different values from 0 up to some maximum value. To understand this concept, let's visualize different situations. Suppose one person is pushing the box with a certain force that is applied horizontally, and this force has a magnitude of F. So then the friction between the floor and the box will be represented by the force, frictional force, that is denoted with a lowercase s. So it happens to be that when we draw a free body diagram for this one, we will have a box to be dot and an applied force this way and a frictional force this way. Since the box is not going to move, we will have net force equals 0, which gives us F minus F static should make it equal to 0. This is the case when the static friction is less or equal the maximum static friction. There's a maximum value. So this maximum value is usually represented as a normal force. I'll get back to that. Now suppose this person is pushing the box even further, even harder. So the force is greater, applied force is greater a little bit. So you have a more frictional force. So that means frictional force is increasing. But it reaches the maximum value of the frictional force. So let's say if we put the free body diagram, now we have a larger applied force, this direction, and the frictional force equal to it, but it's a little bit larger than a previous case. In this case, F net still is 0 because the box is not moving. F minus Fs equals 0. But as you increase the applied force, the frictional force is increasing. So this is where your frictional force, let's say, the applied force equals to the frictional force, and that equals the maximum frictional force, which means the static frictional force cannot get more than that. So if we have to, if we were to graph the situation, I would put this let's say 2 axes, where on the horizontal axis I have the applied force, on the vertical axis I have the frictional force, and suppose that we have maximum frictional force here, static. And what happens as you increase the applied force, the frictional force increases until it gets to a certain point where it is the maximum static force. So this is the situation right here, is the situation where we have the second case, static force is reaching to its maximum. What happens if the applied force is greater than the maximum force? So let's see. Let's say this person now is pushing even further, even harder. So the force, applied force, is larger, but then you have the static force is still at its maximum. So in this case, what you end up having, that your F net now is the magnitude of net equals F minus Fs max, which is not 0 anymore. If the F net is not 0, that means this box will start accelerating, right? And you will get an acceleration. The box will start accelerating on one direction. So if the box starts moving, then we have what? A kinetic friction. So moving box, once the force you applied is greater than the maximum force, then the box starts sliding. When the sliding happens, then the kinetic friction kicks in. Once again, when the applied force is made large enough to overcome the static friction, motion occurs. The greatest or the maximum force of static friction is exerted just before the box starts to slide. And for this case, our just when it starts sliding, in this case, our force, static frictional force, equals mu s times normal. And then right after, maybe it's more accurate to write this equation in the second case, under the second picture where Fs here, or just add here, equals mu s times the normal force, and this becomes a static friction. And then after that, in a third situation that I have when the box is already moving, we have a kinetic friction. Once an object is sliding, the force of friction changes to kinetic friction. I'll put a little lowercase little k, subscript k, meaning for the kinetic friction. And the force acts in a direction opposite to the direction of object's motion and has a magnitude that equals mu k times normal, where mu k is a different number, and it is known coefficient of kinetic friction. It's very important to notice that these two equations that I boxed, they're not vector quantities. If there were vectors, we would have to consider the directions. I mean, this is kind of obvious because F static friction and normal force are in different directions. So we be careful with that. Generally, the coefficient of kinetic friction is less than coefficient of static friction, which means that the force of kinetic friction is less than force of static friction, the maximum force of static friction. So if I have to draw continue my diagram here, then it will look like this. So we have force, applied force is equals static force until it gets to the maximum static force, and then it drops, and from that point on you have a constant kinetic friction, which equals mu k times normal force. So this part is a kinetic friction. This part is the static friction. Applied force is always equal to the static frictional force. Let's note that the force of static friction exists in response to an applied force. The magnitude of the static force and its direction depends on the magnitude and direction of the applied force up to its maximum value, and the force of static friction is equal in magnitude and opposite in direction to the applied force, since there is no acceleration. Thus, if the person were to push on the box in the opposite direction, Fs static force would also change direction to opposite to the box in the opposite direction, opposite to the new push, I meant. If there were no applied force F, then static force would be 0 as well. When the magnitude of the F exceeds the maximum force, the box begins moving, accelerates, and kinetic frictions comes into play. It has been experimentally determined that the coefficient of friction are dependent nearly of the contact area between material surfaces. This means that the force of friction between a brick-shaped metal block and a metal surface is the same regardless of whether the block is lying on the larger side or a smaller side. Finally, keep in mind that although the equation F equals mu n holds in general for frictional forces, it may not remain linear. That is, mu is not always constant. For example, the coefficient of kinetic friction varies somewhat with the relative speed of the surface. However, for speeds up to several meters per second, the coefficients are relatively constant. So for simplicity in this course or in our discussions, we will neglect any variations due to the speed or area and the forces of static and kinetic friction, and we will assume they depend only on the load, which means only on the normal force and the nature of the two surfaces as it is expressed by the given coefficients of the frictions. So here are a couple of examples. Like if you take an aluminum, the coefficient of the static friction and coefficient of kinetic frictions, like for static you have 1.90, for the kinetic there is a 1.40. So let's say glass on glass, for the static friction is a 0.94. For the kinetic, it's a 0.35. You could have a different one, steel on aluminum, steel on steel. Whether it's dry or lubricated, there will be different values. Waxed wood on snow, wood on wood. For example, if you take wood on wood, that will be 0.58 for the static friction and 0.40 for the kinetic friction. So you could find more values of this in your book or any other physics book. Most of the time, the problems that you need to solve will give you these values. Now, unlike kinetic friction, which happens when two surfaces move relative to each other, drag force depends on the speed of the moving object. When I say drag force, it's also known as air resistance or any fluid that resists the motion, drag force. It could be a motion of a ball, like let's say in honey, or motion of an object in air or in a water, something like that. This force is a little bit complicated force. There are several notations for that. Some people, some books denote it as a drag force like a D, or some books use F drag, just simply write drag. It really doesn't matter. And this drag force, in general, the magnitude of this drag force is proportional to some power of n of the speed. So the drag force is proportional to some power of the speed of the speed. To go from proportionality to equality, which makes our life easier, we just write the drag force equals some kind of constant b, v to the power of n. So this is known as proportionality constant. Proportionality constant, and it depends on the size, the shape, and the surface characteristics of particular object, and may also depend on the material through which the object is moving. It's pretty complicated. We're not even going to discuss it in this course. Now, an object moving relatively slow moving object is often well described when drag force is often well described if n equals 1. So pretty much you could say drag force equals b times v. When an object moves at a high speed through air and other gases, the magnitude of drag force is proportional to the square of the speed. N equals 2, and the drag force equals b times v squared. Now consider a ball falling from rest through some air. The ball always experiences the force due to gravity, its weight. So let's just put that here. So at the instant it is released, it begins to accelerate with the acceleration g downwards. As a result of this acceleration, the ball's speed begins to increase. So according to our equation that we wrote for the drag force right here, like I'm circling it now, the drag force, air resistance in this case, also increases. So as g causes increase of velocity. Increase of velocity causes increase in drag force. Drag force or air resistance in this case. This could be easily seen. I know as kids, many of us have done this, although it's not very appropriate to do it, but you probably have taken your hand out of the window while the car was moving. So when the car is moving slower, you can feel the air resistance on your hand. Once it starts moving faster, you can see how hard it is pushing on your hand. So don't try it. I think it's illegal, but you might find a different example to see how the speed increases the air drag. So similar situation is in this case. The larger the speed of v of the ball, the larger the drag force it experiences. If the ball falls for a long enough period of time, the speed eventually gets large enough that the corresponding drag force equals the force of the gravity. Let me draw several situations here. Like, let's say the ball is here. Now, the weight of the ball is always the same. And then because it has velocity initially equals 0, now it has some kind of velocity that is a little bit larger than initial, like prior minutes. Therefore there is a drag force that represents the velocity, and it is like that, for example. So this is the drag force. As the ball keeps on dropping, so the drag force keeps increasing. So here's the weight, and this is the drag force is a little bit larger, and at some point, and the drag force again increases as the velocity increases, speed increases. So, and then the final, let's say there is a moment where the ball reaches to a certain speed. that causes a drag force that is equal to the weight. So here's the weight and the drag force equals to the weight. So pretty much drag force, the magnitude of the drag force equals weight. Here weight is greater than drag force. Weight is greater than drag force in these previous situations. Drag force on the top when it is not moving is 0. Let's not write that. But what happens in the situation, let's say the first situation, net force is greater than 0, so there is an acceleration is present. In a second situation, F net is still greater than 0, so acceleration is present. The next one, the last one I drew, F net is actually equal to 0, where acceleration equals 0. So the moment of this velocity where the acceleration disappears, or we say the drag force equals the weight, the magnitude, this velocity is called terminal velocity. For example, skydivers, when they reach V terminal equals 60 meters per second, they stop accelerating. So they will continue on going down with the same speed. If you take a ping pong ball, this is skydiver, and ping pong ball, V terminal equals 9 meters per second. If you have a parachutist, so parachutist, then the terminal velocity brings to 5 meters per second. That's why when you use the parachute, you land on the ground with the 5 meters per second very safely, and you don't break your legs. We can find an expression for terminal speed by setting the drag force and the weight equal to each other. So if I write for the weight, that is the mass times g, and the drag force, let's say that's a b v terminal squared, then I can say v terminal equals square root of mg over b. So this would be how you find the terminal speed for a particular object that the drag force can be described by a bv squared. The value of b is partially determined by how streamlined an object is. For example, the b value for dolphin in water is about 100 times smaller than the b value of a sphere of the same cross-sectional area. So likewise, a typical car will experience 7 to 10 times less air resistance than an 18-wheeler. Because drag force, such as air resistance, changes as the speed of an object changes, its effects are not instantaneous. For example, the time it takes to reach terminal speed depends on the object and medium. As an example, well, our skydiver who has not yet opened his parachute reaches a speed which is half of the terminal speed in only 3 to 5 seconds. 3 to 5 seconds, half of the terminal speed. And hits terminal speed after 15 to 20 seconds. Another important topic or an example that you see of a terminal velocity, it happens quite often, is when you look at the clouds and they seemingly seem suspended in the sky. Well, certainly the water droplets or ice crystals, which are the high clouds, should fall, and they do. However, they are so small that their terminal velocity is reached quickly, and the very slow rate of their descent goes unnoticed. In addition, there may be some helpful updrafts that keep the water droplets and ice crystals from reaching the ground. Thanks for watching. Stay tuned for more to come.